Hello, audience. Welcome to Skookum Tech Studios Teach Me Something, episode 3. John and I are doing our best to pull this together, hold it together. We're trying to hold it together. And
we're trying to pull it together and hold it together.
Yeah, that's right. First, we got to pull it together, then we can hold it together.
Yeah.
We're on our third episode, and we're talking about John's going to be teaching me something. And as you know by now, the premise of the show is that we teach each other something and you learn at the same time. Today, what are we learning, John?
Okay, today we're going to learn a little bit of the fundamentals of spacing in animation. And because I'm going to try to do a little bit of timing and spacing in animation and what that is and how that can this is used in every single tool that has anything to do with animation. So even in editing programs, and every kind of editing program has these little tools in there, and a lot of people don't know what they are, and they are they're like kind of in the fundamentals here of animation. So we're going to look at some of those. We're going to look at some of those tools in an advanced program, but that will actually be applicable in all of these other programs as well. So that's what I'd like to do.
This is perfect because I don't know the first thing about those concepts, so I'm really going to learn something. I'm poised and ready to learn, John.
All right. This is Maya, and it's a very advanced, it's an industry standard program for creating animations, but we are just going to look at a concept here, and we're going to kind of get rid of this for a second. Let me color these real quick. So we're going to take all these guys and we're going to move them from this location to this location. And we change the timeline down here, so they're going to do this, right? Okay. So if we watch this, it's pretty quick. Here, let's do 24 seconds. So maybe we can get our 24 frames, so we can get a little bit more context. So I'm going to move this over here, or a little bit more visual understanding. Okay, so what's happening right now is these are we've animated these based on a regular, any kind of program. You can put a keyframe over here like I just did, and that's what this little red indication is over here. And then I can go over here, I can move the objects, and I can put another keyframe. Okay, this is the basics of any kind of animation. Just 2 keyframes. I got one here, one here. Now I can put one in the middle here, and I can move these up, and now it's going to do this. Okay. Wow. Okay. So this is what I want to talk about is a lot of I want to talk about how to understand this movement and understand in programs what is actually happening by default and how to control this. So right now, we're going to look at these 3. We're going to just take one of these little spheres for a second here. And what you can actually see is initially what we actually did is we moved this ball from left to right, right?
Right.
And so when I move that ball from left to right, this program is specifically designed and geared to kind of automatically do an ease in and ease out, or sorry, an ease in, a quick, like a normal line, and then an arrive to. So let me explain this. All in animation and any kind of program like this, the objects, every object that you move is actually just a position in space that is an XYZ. So you see the XYZ little arrows here. And so this is the Z. This is all basic kind of 3D space. We're dealing in 3D space here. So I want to go from this X over here, and let me get my little channel box up here. So I'm going from X0, you see over here, X0, and I'm going to go all the way over to X, 14.075. Okay. Now this is representing that. So if I select here, this is 24 frames up here, and over 24 frames of time, I'm going this number right here, 14.75, and I started out at 0. Okay. So this is now how it's getting there. This is the interesting part. So I could actually change how this particular ball, I could change how this gets there. It could start off going super fast and then slow down as it arrives. See that? Does that make sense?
It sure does, yeah.
Okay,
And
so
in
that's
the
going to go.
programs that I've worked with, I think more of the programs than not will start off with a linear motion. And if you want
Right,
it to ease, you have to go choose it. So it's interesting
right.
to me that Maya chooses easing by default. I think that's the right choice.
Yeah, yeah. A lot choose easy by default, a lot choose linear. And so it depends on, yeah. And so a linear, like the first basic, most basic would look like this. It would just be from A to B. And now let's watch this, how different this is. So let's take the let's take the hitch out here, because that's going to confuse us for a bit. And let's just look at these. So this ball is still arriving at the same time. It's leaving the station at the same time and arriving at the same time, but it's just doing it linearly, and these are easing in and out. Okay. So when we look at that, we can look at these. Let's look at both of those, and we'll just look at just the X, because that's all we care about right now. So with those two, obviously, like I said, one's doing that, one's doing that. Now let's grab this purple one. That was a good explanation. One's doing that, one's doing that. This one is doing the linear thing. This one's doing a little bit of an ease in and out, but let's exaggerate this ease in and out so we can really get the effect. So this would be an ease out overshoot. Maybe
John,
I can't.
can I read something to you?
Sure.
So there was something intuitive about this. I haven't thought through this very much, so this is really fun to see this and talk about it. But it in my mind, I was saying there's something about this kind of motion that matches with the laws of physics, and I think it's that your body, this body that you're moving physically, can't get started as quickly as it would have to with linear or even the other kind of motion that you illustrated. And AI comes back with me and says, well, when the ball goes from rest to full speed in a single frame, its velocity changes instantaneously. And acceleration is the change in velocity over time. And if that time is 0, the acceleration is infinite, which would require an infinite force acting on the ball. And so that linear line is a constant acceleration, and it goes from 0 to full acceleration instantly. Right. And that's not possible. That can't happen.
Right. Most things do. They ramp up because of weight, and then they get to a certain speed, and now they've got to slow down.
Yeah.
And this is the representation of that in a line here. And yeah, that's a really good point. Yeah, and this is all has to do with physics. Like, we're all dealing with real physics, and we're trying to implement and fake real physics and fake the viewer, fake out our viewers and audiences that this thing is heavier than it should be, or sorry, it's either heavier or lighter or whatever, right?
Yeah.
So and the way you do that is through timing and spacing. So based on what I'm doing here, what is your expectation of what this ball is going to do?
It just seems like more easing, but I don't know why you added another key instead of grabbing that Bezier handle on the end node and just manipulating it.
Yeah, so you can see this, like, sometimes weighted handles, you can drag this handle and you can drag this handle out and it'll actually do that.
Yeah.
But I don't like weighted handles because they don't. If I have like 1,000 keyframes here, I'm trying to keep up with like which ones are weighted, which ones are not, and I'd rather not do that.
I see.
I'd rather them all be kind of like consistent and they can only go this far, and then I control it with keyframes.
Okay.
So yeah, that's the answer there. But yeah, like I couldn't actually do what I just did. Like if I do this, it's gonna go up. See that?
Mm-hmm.
So I can't actually, the only way I can get this to go even more is by adding an actual keyframe.
Yep.
Okay. So this most any kind of heavy object takes a lot longer to get moving,
Mm-hmm.
right? But then once it gets moving, it can move pretty fast. And then, but it also will take more time to slow down. So let's look at our objects now. So this top one here, it starts slow, moves fast, and then takes a second to. Now it kind of looks like that one's actually fast, compared to these guys. These guys
Mm-hmm.
actually look kind of slower, don't they?
Mm-hmm.
But the linear one is actually doing something completely unfair. It's starting from like I'm the fastest person in the world, and
Yep.
they're bolting. So that's
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 exactly what I was talking about. It's starting out with its full
yeah,
speed.
it's starting out at like already going 10 miles an hour, 20 miles an
Mm-hmm.
hour.
Yeah.
Um, and this one's just easing in and easing out. It's a little bit lighter. It's a little bit lighter. But this one is heavier. You can feel it.
So that communicates the weight of the item to the viewer, is that right?
Right. And so yeah, things take the heavier they are, like the more that they're gonna the more frames or the more time they're going to take getting up to speed and then getting back down to stop,
Mm-hmm.
you
Mm-hmm.
know, anything. And that means like a hand, or if you think Godzilla, it takes a lot for Godzilla to pick up that leg and then
Yeah.
put it down.
Yeah. Even though
Um,
he's strong enough to do it, it's still heavy and it still has to obey the laws of physics if you want to deliver
right,
it.
right. And like just because he can, or even King Kong, like King Kong can actually get running and go pretty fast, but it takes him a lot to get running, and he's huge and heavy, and all that mass, it takes a lot of energy to move and a lot of like strength, and um, I mean, King Kong's a little unrealistic, but that's why you'll see like, the brontosauruses in Jurassic Park move really slow, you know, because moving that much mass, it takes a lot. Takes a lot.
Mm-hmm. Yeah.
Um, and yeah, there's kind of like a debate, not a debate, but like once things get, some big things, like there are big guys that can swing hard, right?
Yeah.
Um, but big guys in general, like one of my favorite to think about this, and I wish I had brought it up, is in Princess Bride, you got Andre
Andre.
the Giant.
Yeah.
And he's fighting the little guy, and the little guy's going all over the place, and Andre the Giant's like trying to grab him, and he's big
Yep.
and slow, and you can, yeah. So I
And
love that example.
you
Yeah,
met Andre's daughter.
I did.
Yeah. When you were working at Starbucks, she came through the drive-through. You told me the story. You don't remember it?
Really? I
Yeah.
don't I don't remember this. That's funny.
That's funny that I do and you don't.
That is funny. Okay, so in most programs, you won't really get a curve like this. You won't get control usually with these let's do these three. So you won't get control of these curves in a lot of
Mm-hmm.
programs. So what you
Yeah.
will actually get is you'll get these little symbols up here. Do you see these?
Yep.
Okay, so this is true for like well, actually, I was going to bring up After Effects, but After Effects just says ease in to ease out. So let's do something here. Um, let's take this one. So After Effects will say something like this. It'll say ease in, like ease in. So this is just to ease in, and then it's going to go straight on till morning. It's
Yeah.
just going to, yeah. That's an ease in. And that actually doesn't look great when you stop something that hard. So let me get this by itself here. Yeah. Oh, you feel that?
Yeah, sure.
Now the
Oh,
start
how did that happen?
the start is nice, but then you're like, that feels wrong. Like
Yeah,
that feels wrong. And
yeah.
in the animation world, we call that hitting a wall.
Well, and I think that in my brain, I can feel right now as I watch it that it really does communicate to me that this thing must be so light in order for it to stop that fast. It
Well,
must be a
but
bubble, you know?
even if it's the lightest
Yeah,
object in the world,
yeah,
you cannot do this in real life.
yeah, right.
Like this object either bounces. So let's do this. So this object, let me get this down a little. So this object does usually one of two things on average. It eases in. We've already shown the ease in, right? So we know that the ease in. This is easing in, and it can do that. That feels better,
Yep.
but it can also overshoot. So if it's moving really fast, it can overshoot that object and then come back
Yeah.
to its place, and
You, you've
that
even
will
you've
so
even got
that
it kind of overshooting and then bouncing back. You could drag that handle back down and create a little back motion as well.
well it is going past our point and coming back here.
Yeah, what I mean is it's going past the point and then on the way back, you could pull that handle down and have it rebound just a little bit more and then finally settle on that last point. Not that point, but the left Bezier handle.
This
Yeah, drag that one down. No, no, down. There you
like
go.
that.
Not that one.
Oh,
Yeah, but like that's a little bit much maybe, but that would look like it's an elastic landing. You know, it's going past it and
right.
bouncing and then landing there.
Right. And so that feels really aggressive, right? So
Yeah.
we would actually want to drag this out and do a proper. But see, normally when things bounce, they actually they actually peak. They actually so you break these. So let
Yeah.
me break
Turn it
these.
into a cusp.
Well, you know you can look, see how I'm doing this? So
Yeah,
I'm breaking.
isn't that a cusp node?
I don't know. It's not a node. It's just breaking the tangent. So like what this program's doing is it's saying these are I'm going to move these curves along
Hmm.
a they're going to tangent based on these handles here, these
Yeah.
little white handles. So it's
Yeah.
always going to be tangent, but you can break those handles, and so you can break that tangent control, and then you can do
And
something like
in
this.
the applications I've seen, it calls the former where there's a tangent, it calls that a smooth node, and then when you break it, it calls it a cusp node.
Oh, yeah, I don't know about that. I've never heard that, but maybe that's right. Maybe that's right. Um, But the principle is like if you're going to hit a wall and come off of it, then you are going or you're going to hit the ground. You are going to probably it's going to be something more like this.
Yeah.
You're coming at it, and
Yeah.
then you hit, and then you bounce off. So you're
Because
not doing
if you smooth right up to it, if you ease right up to it, that easing communicates that you have lost all energy. There's no more energy to bounce.
well, yeah, and it gives it like some sort of character because you're like saying this character understands that it's going to hit something and it needs to slow down. But like a
Yeah.
ball or something like a car doesn't understand or isn't doing that. It's gonna
Yeah.
hit, it's gonna go until it hits
Right.
this wall here. So okay, so yeah, so this one we got a little bit of a, but even that feels better than the direct to stop, right? Like, oh, like that this still feels better than what we were doing here where we go straight to a dead stop. I mean, that just feels awful. And so you should never do this. You should never do this. You should always either ease in or do an over like do what we just did, bounce and come back. There's a lot of different ways to treat this. Let's see. or this guy. The other, yeah, so you can, let's see here. So the one way is that, oh yeah, I guess we did do the overshoot. Yeah, so if you're going to overshoot, it is kind of like what you were saying, Jeremy. It is a little bit better to kind of really settle it, you know?
Mm-hmm.
Like if you're going to overshoot, you got to be careful with overshoots because they can feel pretty ziggy zaggy, you know? And I think you need more time here. So, oh yeah, but this also we're not bouncing. So yeah, I was just trying to think of like if you were bringing in titles in something, you
Oh
know,
yeah.
and you had titles coming in from like a shot or something. You don't like you usually would never you would always ease in on a title. You would never on average overshoot unless it was a funny movie.
Yeah.
If it was a
Oh, I
funny
see.
movie, you could overshoot you could overshoot and then come back. But yeah, on average, if you have just normal titles, you would like kind of like, and the thing about titles is you could come in off screen by not easing in. You could come in full speed here, like using linear, right? And
Mm-hmm.
then come in and ease into it,
Mm-hmm.
you know?
Yeah.
So you could do
Yeah, because
that.
it's coming from off screen, so the viewer doesn't know what happened to get it going, so it doesn't feel wrong.
Right. So it doesn't feel wrong.
Yeah.
Exactly. Yeah.
So let
So,
me let me teach you something here, John, that I just looked up and I think is interesting. And
sure.
um, so you know that for me, school involved a lot of math, and I'm kind of a math guy.
Oh
And
yeah, there's a lot of math in this.
there is. I was actually wondering if you had more collegiate level math, if that would really round out, because a lot of your training and skill and experience is in art. And if you took some math classes, I bet you would have a lot of aha moments, you know?
Yeah, like this obviously is like, like when I took trig, all of
Hmm.
this makes a lot of sense because in trig you're trying to like calculate where the points are, here's your grid,
Yep.
and in trig you're trying to calculate like, okay, well, x plus y this, and it puts the point up here and then there's a point here and then you kind of graph the points.
Now, did you ever take any calculus?
I never took any calculus, but I do know like about the theories of calculus to
Yeah.
the
Okay,
degree that
good.
it's like the volumetric of the volumes
Right.
of this, right?
Right. And so this is something that I just learned, and so I want to share. So I knew this part. So you think about that ball's position, and
Yeah.
then its velocity is its first derivative, and its acceleration is its second derivative. So there's that mathematical function that you can do. You could just run the derivative on a function and get from the position to the velocity, from the velocity to the acceleration. And I learned that there's a third derivative and there's a term for it. It's called the jerk. And so the velocity is, so here's the way this says it. It'll say it better than I can. Velocity is how fast your position changes. Acceleration is how fast your velocity changes. And jerk is how fast your acceleration changes. And
Hmm.
so it's what you actually feel in the car, because if you have constant acceleration in a car, your muscles all adapt to it and then you feel comfortable. It feels to you like nothing's changing because your acceleration is constant.
Yeah.
And then when all of a sudden that changes and somebody slams on the brakes, your muscles have to adapt to that. And so that feels uncomfortable, and that's jerk.
Mm, mm. Yeah. Um, I don't think I that's interesting. I do like the math of all that stuff. I think we've talked about shooting a gun out the window at a
Yeah,
target,
yeah, yeah.
kind of things like that. I think like in animation, like in general, when you're just trying to animate, you do need to understand how physically that could not, um, how physics would work with
Yeah,
stuff like this
yeah, yeah, yeah.
and how
Yep.
like one of the biggest problems that a lot of people have when they start animation is like especially when they start making characters is they tend to pick up a character's foot while his weight is on it.
Oh, wow, interesting. Yeah.
So I think I could bring up a character
You told me
to do that,
something
but
while you're doing that. You told me something a long time ago, which was that if I'm watching a movie and something flies by and it doesn't have a shadow being cast underneath it, I
yeah.
might not notice that. You might say there's something odd here, and I'm, asking you to find it. I might not even be able to find it, but subconsciously I go, there's something that doesn't look right about that film.
We actually don't know until I put something of real scale how fast this is actually moving. Like, I don't really know. Like, if this is actually like a meteorite and it's going from here to here, I don't know. Like, maybe it's huge, or maybe this is just a tiny thing rolling on a desk, So context really matters. And one of the problems when they were initially making all of the flying movies, like there was you couldn't tell what was going on with the planes. You needed a backdrop. So every flying movie has clouds or has clouds around it.
Yeah.
Any kind of plane movie, because you need this context in order. And it's funny because when I jumped out of a plane, when I actually jumped out of a plane and parachuted, there were no clouds, and I just felt like, I don't know, I guess it's windy, but I
That's
didn't
how
have this.
that's your frame of reference.
Yeah, and I was like, the ground's sort of getting closer. I mean, sort of, like, I guess, but not as fast as I thought. And so I just had no frame of reference, where I think actually bungee jumping a little bit scarier because you have this frame of reference. So
Mm.
anytime, so scale in art is like a big deal. Yeah, and here's some examples. You can see how these are moving. Let's see this guy. Um, you can see how I've done this. So it's this x-axis here is going this way until it hits this wall, and then it's going to bounce around and kind of do its thing. And then what it's actually doing is the y is really interesting on this, because the y is doing what you think. It hits here,
Yeah. Yeah.
and I don't know if you can tell there. It's kind of so that it's going to hit, it's going to bounce, and it's going to make that corner like we talked about. And then it's going to come up here, and as it gets to the top, it's going to have this nice soft. There's a lot of frames up here because it's fighting gravity. It's fighting gravity, and then it's like coming down, and then it hits, right?
Yeah.
So the weight, and now this weight, look at the weight of this versus the weight of this little guy. So this little guy, look how, now I did use weighted tangents here. See how fat this is at the top? Can you see
Yeah,
that?
right. I do.
So
It's the first thing I noticed, actually.
yeah, so these ones, like this, not as fat at the top, but this one, it'll be really fat at the top because it's a lightweight little object, and it's gonna take more. It can get up there quick, and then it's like, it's gonna spend more time in the air because it's lightweight. And then it'll come down and it'll hit and bounce, and yeah. But this guy, look at this guy. This is the heavy ball, and it spends no time bouncing around.
Hmm.
It's just gonna come down, and it's gonna come down and just hit and do a tiny little bounce, and then one more little, like this is even a tinier little, yeah, this is even a tinier little bounce, and then it's gonna level out.
There was a project I was just looking for. I had an IoT device with an accelerometer on it, and I set it to record all of its data. And then
Okay.
I was working on a device that I was going to package up. It could be fired up, and then when it reached the very top of its travel, it
Mm-hmm.
would deploy a parachute.
Mm.
And in my brain, and I feel like a dummy now, but in my brain, I was thinking that my graph would show me very clearly where the top of this travel is. And so to prototype it, I made this thing, set it to record, threw it up in the air, and then I caught it. And then I looked at the data, And it did not look at all like what I thought. I was kind of expecting something like this, oh, there's clearly the top. All I have to do is calculate that. Not
Yeah.
at all the way it works. In fact, what
Huh.
do you suppose it looked like?
You just threw up in the air and it was calculating like the distance, and it was like a perfect gyrus. It was calculating
It,
everything.
it was calculating its inertial change, basically, the way that the way that the little chip in a 9 degrees of freedom chip will work, just like the chip in your phone.
Oh, okay. Yeah, I don't know how that calculates. So I mean, if it could actually calculate, the distance and the velocity and all that stuff, I would assume it would look like a
Well,
curve.
it can't measure distance. It can't measure translation. That would take a different kind of device to say, oh, I've gone this far. It can't do that. All it
Hmm.
can measure is inertial changes. And so imagine you're just holding the device right there. It would sense gravity was tugging on it constantly. And then
Right.
if you moved it to the side and then you looked at the change in x acceleration, you would see that it went up and then back down, right? Because I moved it and then I stopped it.
Hmm. Hmm.
So I was looking at the y acceleration value when I threw it up and I caught it.
Yeah.
And I was surprised to see that the acceleration in the y direction was constant. And that's because as soon as it left my hand, like when I was throwing it, I was imparting a force upon it.
Oh, yeah. So it was sort of leaving your hand linearly, or not linear, but well, it was fighting gravity, so it should have been slowing down.
Well, I was overcoming gravity as I was throwing it, right? So
Right.
it went
Right.
from a constant downward force to an overcoming upward force until it left my hand, and then all upward force went away, and it was only under one constant force again, and that's gravity. And
Yeah.
the
Yeah.
entire travel, even at the top when it slowed down, reached its peak and turned around and started falling. That entire time, it was under one constant force, and that's just gravity. And so that y-axis acceleration told me nothing about when
Oh.
it reached the peak. Nothing at all.
Hmm. Yeah, I think you'd have to measure that externally
You did.
to,
Yeah, I'd have to measure it using a high accuracy barometer that
yeah.
measures a slight change in barometric pressure. That's the only way I could measure it.
Oh, wow. I mean, I think visually you could measure it, but
Oh yeah, yeah, that's right. I see what you're saying. Like if you captured it
yeah.
on a camera, you could
Yeah, you
analyze
capture
the
it on a
frames, but you
camera and then
can't.
you could kind of, yeah, then you could do math and stuff to figure out. But yeah, and everything, I mean, that is kind of an interesting thing. Like everything has every weight, aside from, we all know that if you drop a bowling ball and a feather and a vacuum, that they'll land at the same time. But
In a
um,
vacuum.
yeah, in a
At
vacuum.
first my brain thought you said if you drop a hammer and a feather and a vacuum.
And a vacuum. If you drop a vacuum inside of a vacuum, what do you think will happen? Um, Yeah, so yeah, we all know that, but you have to get used to, especially so for beginning animators, if you're trying to, or just any person who's trying to get into like motion and stuff, if you're trying to do that, you've got to study other people and you've got to study real life and look at this stuff. Look how long it takes a kid to get to that soccer ball and then kick it, and or how is he getting there? He gets quick, then he slows down, then he kicks. Like there's always these ease in and ease outs everywhere you look in life, and to pay attention to those and to understand that.
So this is an old blog of mine, and this was the contraption. It was supposed to connect to a GoPro, 3D print this
Oh,
box. Can you see it?
yeah, yeah.
Yeah, 3D print this box and then put the device inside the box and have a little switch on there that you actuate from the device that pops open this lid and the parachute comes out. So the idea was that you launch this GoPro into the air and then the parachute comes out. Let's look at the date on this article. 2014. This is a long time ago, in my defense.
Nice.
This is
Nice.
before we had, $400 drones that you could send up and get a really nice video for you. So the parachute would come out, and then the GoPro would slowly drift down, taking a video of whatever was beneath it the whole
Oh,
time.
I see.
Yeah.
So
that
you're going
was
to
the
shoot
idea.
this, you're going to attach this to some rocket or something.
Well, I was going to use a slingshot.
A slingshot?
Yeah.
I don't think you get
I
it
didn't
very
need it to
high.
go to outer space, John.
I mean, look at the size of that thing. You got to get a sizable slingshot for that.
Yeah, maybe you're right. Well, maybe this is why it never shipped. Okay, so there's the code. There's the graph. There's the acceleration. And you can see when it left my hand right here, this was the time in the air. And then this spike was when it was landing in my hand and slowing down very quickly.
I do not understand. That is weird to me. That's not helping my whole analogy here, but
This is just me. And actually, this is the overall acceleration. So this is all 3 dimensions.
but is it like, I guess I need to look up how accelerometers work, because let's say you chuck it in the air, you're not chucking it perfectly flat. Like it's going to spin and turn a little bit. So that's going to cause some...
spinning and turning shouldn't do very much inertial change on the chip.
But if it's inside there, yeah, I guess I need to know how this works.
Some of the sensors in your iPhone are good at determining when it's been rotated, but that's not what this one is doing. This chip is only measuring how quickly you moved it in X, Y, and Z directions. And in this case, it's putting all 3 together.
But it's also yeah, but if it's spinning in the air, how's it? I think
the spin might be this little jitter that you see right there on that line. If we could zoom into that,
yeah,
that might be what you're looking at. That waviness is just it spinning while it's in the air. Because it's weird. If it were spinning perfectly about that sensor that I put in it, this thing, if it were spinning perfectly about that, it wouldn't register any at all. But because that's not in the center,
it was oblong.
Yeah, right.
Yeah. That's interesting. That's pretty cool that can actually even measure that, though.
Yeah, it is cool. You started off saying, I'm going to teach you about spacing. Where does the word spacing come into what you taught us? Because what you taught me, it feels like kind of how to start and stop motion, but you said spacing. Yeah. What does that mean?
Yeah, so the principle of spacing is that I'm not sharing.
No, you haven't been sharing for a long time. I don't know why I didn't.
What? What happened? Okay. So you see this? Can you see this?
I can see it, yes.
Okay.
That's exactly what I was thinking too. I guess it's because I was visualizing it really well as you were talking.
That's great. So this would be the first frame. This would be the 30th frame. This would be the 15th up here. And then if you needed, like, then you would kind of go, okay, between 1st and 15th, I'm going to draw this circle. And so I know, okay, halfway, I know that there's not going to be a lot of frames in here because it's coming down as fast as it is over here. But I know it's going to build up. Now, 15's wrong. This is actually, let's see, 1, 2, 3, 4, 6, 7, 8, 9, 10. So it's 20 to here. So it's 1, 20, and then this is 10. So I know that I could put, this third one over here, and then I can put another one at the halfway point, and then I do another halfway. And so you basically just kind of divide it up by halves, and there's a whole method to that. But in 3D, we don't have to do this anymore. It's very good to know. It's very good to know. You still kind of do it mentally in some cases, but for the most part, you do want to do this right, though. And the more bouncy, everything is a bouncy ball. In fact, a lot of guys will animate a whole character coming down a hall and doing stuff just of their pelvis, and their pelvis is just this bouncy ball, like kind of moving around. and they'll get that bouncy, or they're fighting with somebody and they'll have just a bouncy ball and like a cube as a torso, just to like get all the movement and get that looking right and bouncing around right and stopping and slashing and stuff. And then they'll add the arms and the legs and everything. So yeah. And the timing thing, yeah, I don't know. I mean, this, yeah, so you can see like those are the frames behind. And then there's a lot of frames when it gets to,
Yep.
There's a lot of frames when it gets down to that. Let's see. Change this. Yeah, so this is just a ghosting feature, and it does help you understand where things are coming from and where they're going and stuff. In here, we would do something like, oops, like this might make it a little bit more obvious. So you can see they get a little, now this is pretty even. When you see this being this even, you know something's wrong with your animation.
Yeah, right.
So you want to always do the ease in, ease outs. And that's the main lesson. But yeah, ease in, ease outs. If you're coming at something super fast, it's got to have it is hard physically to stop my hand at exactly this spot without shaking or doing anything. It's very hard to do that. I overshoot and then come back. And we exaggerate everything in animation. So, you know, if you punch, it recoils afterwards, it stops hard and it recoils. And that's a lot of animation is that, so yeah.
That's fun. I like those concepts. It's like learning to recognize reality.
Yeah. And the more you like actually kind of out in the world look at it, the more you'll like go, oh wow, I can actually create that. Even if it's a title sequence of your little, video that you're doing at home, it's very nice to have those subtle ease in and outs,
Yeah. Well, John, you felt underprepared at the beginning of this, but that ended up being wonderful.
Cool. Well,
so thanks everybody. I'm going to go ahead and say goodbye. Thanks everybody for joining us on this episode 3, Teach Me Something, where we learned about some animation principles, spacing and easing and lots of cool stuff there. So join us on the next one. Actually, I think I can queue up the next one because I think I'm pretty confident about what I'm going to be teaching. I'm going to teach about some Git and coding concepts, and specifically when you're using agents to help you to develop software. What if you want to employ multiple agents and they want to work in the same code base? And so they're going to be touching the same files. And there's a very easy way to do that. And it's called work trees. So we're going to learn about Git work trees next time on Teach Me Something.
Okay, I love it.
All right. See you, everybody. Bye, John.
All right. See you, everyone.